Hello and welcome back from your weekend. Today we're going to switch gears and look at regularization. And so the reading in general are from Chapter 4 for these modules that we talk about, including last time what we covered in overfitting is Section 4.1, Section 4.2 of the book of regularization, and Section 4.3, which is validation. Please look out on the blackboard. There is a homework. Homework number 2 has been posted. It is a written assignment. It is due a week from Tuesday, which is the 31st of March 2020 at the usual 1 second before midnight, 11:59 and 59 seconds. Please make sure you look at that. And for that work, you can do it handwritten and scan it in, high quality scan. You're welcome to do that, but please make sure it's legible. If you have access to a printer, print it out and make sure it is legible. That's the most important thing. Okay. So last time when we talked about noise and complexity, we looked at, to jar your memory where we left off, of the behavior, overfitting behavior of a complex model, degree 10 polynomial, relative to a simple model, degree 2 polynomial. And we were looking for this red region, which corresponded to this final best hypothesis G10 overfitting. And what we saw in both cases, we varied the noise level of a fixed complexity polynomial target function, and we varied the complexity of a fixed noise target function polynomial, and we saw that the overfitting behavior looked identical or very similar to one another. And we concluded saying that stochastic noise, as you increase the number of data points in general, overfitting goes down. As you increase stochastic noise, which is your graph on the left of the screen, overfitting goes up. And if you increase deterministic noise, the complexity of the target function, overfitting also increases. And so we left off with this motivation for how you deal with noise in the prime topic for today, namely regularization. And so we have a noisy quadratic target function in the blue, and we have a fourth order polynomial hypothesis set in the red. And so in sample, we see that our hypothesis set fits precisely all of the points sampled from our noisy quadratic target function, and that you can see because it pierces directly each one of these data points perfectly. And the idea is that it will have high out of sample error, because if you look at all these distances between the target function and the red curve, you add all of them up, that's going to be a pretty large number. But if we restrain the fit, then we get something that looks like this. It's a lot smoother, and you'll observe that out of sample, these spaces between the red curve and the blue curve, it's much smaller. And so there were two approaches that we left off with, two approaches for dealing with noise, and one is through validation, and in effect you're simulating or estimating out of sample error and using that to guide your model choices. And the other topic of today is regularization, where you're restricting the hypothesis set in some fashion. Okay, and so let's take a look at the intuition. And there's a mathematical approach in function approximation that kind of motivates what regularization is and what regularization does, and it pertains to so-called ill-posed problems. Now, an ill-posed problem in function approximation is one for which you can have many solutions. And so how you deal with this in function approximation is to put smoothness constraints on your solution and then solve, right? And smooth approaches tend to be, or smooth solutions tend to be better solutions. One way of doing this in the Bayesian standpoint, or from the Bayesian perspective, is to encode a prior distribution, adding kind of a smoothness criteria over the possible set of solutions that you could consider, and that prior effectively guides your optimization with the domain knowledge you have encoded. And so that Bayesian approach generally smooths or produces some weighting, if you will, across various solution types of solution that your model would consider. And so what this regularization deals with is effectively handicapping your optimization problem. So what you'll see in our considerations that you add a penalty term to optimization, and that penalty term guides the selection of solutions or feasible solutions by your optimization, such that it prefers solutions that are smoother. And so you add a penalty term to your optimization, and then you calculate the gradient of in-sample error, trying to drive that to zero, solving for that weight vector that satisfies En to zero, but also minimizes at the same time that penalty term that you've added. And so in doing that, you're satisfying two things. You're minimizing in-sample error, but you're also guaranteeing that you don't incur a lot of penalties, because that penalty will cause En to be bigger if you do not satisfy whatever is encoded by your penalty term. And so we had this example before, and we'll just kind of pull it up and reshape it from a regularization perspective. And so on the left-hand side, we had the unconstrained model. We had 2 points, to jar your memory, that were sampled from a target function. The target function is a sinusoid. And then we fit a line to these 2 points. Now, of course, based on where you sample it, you're going to get different lines. Some lines you can see are much more kind of wildly sloping, and other lines tend to be more smooth, those lines corresponding to regions along the center here, about the between pi and 3/4 pi radians, if you will, in the sinusoid. But nonetheless, we have a lot smoother lines that don't slope quite as dramatically as the lines at the extreme. And with regularization, what you do is you put constraints on the parameters associated with the hypotheses or the lines on the plane that you would consider. You would say, okay, well, let me put a constraint on the slope and the y-intercept. Now, if you put a constraint on the slope and the y-intercept, your lines will not pierce the y-axis as high up or as low. And if you put constraint on the slope, well, this is kind of a smoothness constraint. It's not going to be sloping very high. It's going to be a flatter line, if you will. So in that second solution with constraints, you'll notice that those lines that are very high or very low on the y-axis are not selected by the optimization or by the learner when trying to fit the line to the 2 points that are sampled from the target function. And you'll notice also their slope is not as dramatic, right, because it's only considering slopes within certain regions. And so with regularization, you can see and you can verify with bias and variance analysis that this leads to better models. Okay, so let's do that. And so the gray shaded region represent for the left-hand graph. The left-hand graph represents the unconstrained model, and the right-hand graph represents the constrained model with regularization. And as we had done before, we take all of our solutions and compute the best average hypothesis G bar. So literally, we're taking all of the lines for the solution and taking the average, and this is the red line, our G bar. And then the region carved out, if you will, covered by all the different solutions, that's the gray area, and that's what we're going to use to measure the variance, so basically the width of this gray area. And so here we see G bar goes right through, and it seems like it kind of fits nicely, tries to fit very well the general arrangement of points you could sample from this target function along the sinusoid. But one thing we do see is there's a very high variability. This gray region is very wide. And if we were to actually numerically calculate this, we'd have a bias of 0.21 and a variance of 1.69. So things get pretty bad if you think of the sinusoid as being between -1 and 1. That's pretty bad to have a variance of 1.69 when you consider the sinusoid on the unit circle. And so on the right-hand side, in our constrained solution, i.e. the solution we've used with regularization, for which we've used regularization, we notice that this gray region is much more narrow, right? So the variance is smaller. But we also notice that if you take a look at this G bar, our average best hypothesis for the regularized solution, you notice that's a little bit further down. The bias is different. And so we've kind of shunted or lessened the descriptive capability of the hypothesis set when we limit the y-intercept and the slope to a smaller range of values. And so that manifests, you see, the bias is a little bit higher, so we sacrifice some of the bias. It's less descriptive, so it can't twist, bend, and fold as rapidly as the unconstrained version in trying to mimic the ground truth target function. But nonetheless, if we look at the variance, it's much narrower. The variability, the variance is smaller. And if we add bias to variance, we'll see that this regularized version is superior in its performance because it's much less. Okay, and so regularization decreases the variance with a modest increase in bias, and essentially by handicapping the fit, it resulted in a loss of quality of fit, but we more than paid for or benefited by handicapping the fit by lessening the variance. And so essentially, when you want to describe the sinusoid, you have a bunch of choices with the linear model. You can have a constant line, straight line across. You could have a quadratic, or you could have something that's linear, or something that maybe mimics aspects of all three. And so this idea of mimicking aspects of all three is exactly what regularization does. And I'll explain more about that in a few slides. So let's take a look at the formulation of regularization. And to do that, we're going to use a polynomial model. And in doing so, we're going to define a phi function that's going to map from your input representation to a polynomial representation. And so let's define the transformation that consists of the Legendre polynomials. And so this is a polynomial mapping, and it's going to be polynomial of degree q. And so in doing our linear regression, we're going to have a polynomial regression model through a transformation into feature space or z-space, and then we're going to do a linear regression in this z-space. Okay, so in the z-space, our hypothesis, h of q, where q represents the degree of the polynomial, so the bigger q, the more descriptive this polynomial is because you have higher order terms, and this Legendre mapping is a method for getting this polynomial so that each one of the terms, the first order, second order, third order, they're orthogonal to one another. And I'll leave it to you to look up Legendre polynomials in the literature. But nonetheless, our hypothesis set is the set of degree big Q polynomials. And so we have a weighted sum WQ, the weight for the Qth term, WQ times that polynomial term for the Legendre polynomial. And so this is an example of what they look like. This is the first Legendre polynomial, this is the second, this is the third, this is the fourth, and so forth. And so you're going to have terms that are first order terms. You have x to the 1, x to the 2, x to the 3, x to the 4, x to the 5, and so forth. It's just another decomposition for what a polynomial is. So let's take a look at the unconstrained solution. We're going to be given our input data representation, x1, y1, x2, y2, up through and including xn, yn. So we have our original input representation feature vectors along with the labels. And so we're going to transform this into z-space through our polynomial mapping using the Legendre polynomial. And so the more complex the polynomial through the mapping, the more complex the data representation. And so our in-sample error now is, as we're using the L2 or the squared error loss, is just going to be the average squared error loss now in z-space instead of our x-space input representation. So we have En of w is 1 upon n times the sum. For n goes from little n goes from 1 to big N of w transpose zn, where each zn corresponds to each one of those xn's, minus y, quantity squared, because we care about the magnitude of the difference, but not the sign. Is it positive or negative? So then we can convert this to matrix vector form by transforming it with a design matrix, where each row of our capital Z matrix is one of these data points in Z space. And so Z is going to be a row matrix, and you're going to have Z1 as the first input, Z2, Z3, Z4, and so forth. And so the minimization problem for minimizing in-sample error is 1 upon n, so ZW minus Y quantity transpose ZW minus Y. Okay, and so of course ZW minus Y transpose, something transpose times itself, is in vector matrix format, the way you square something. And of course, like we had done before, if you solve this minimization problem by setting the gradient equal to 0 and solve, you get the linear regression solution that we will call W-lin. And that's the pseudo-inverse. So Z transpose Z, quantity inverse, Z times Z transpose Y. Okay. So let's take a look at these constraints. So if you think about hypotheses, one way of constraining a hypothesis, if you're thinking about a polynomial, right, and let me go up here, you could have a polynomial like say, let's say you had a polynomial W, let me select the pen colors, say blue. So let's say you had a polynomial, and your polynomial is say WQ x to the q power, right? W1 x to the 1 power plus W0 x to the 0 power, which is just 1, right? So that's the general form of a polynomial. And if you think about what a degree 2 polynomial is, let's write in the W2 x squared term, right? That's nothing more than a special case of a degree 10 polynomial where each one of these coefficients up to and including the W3 is set to 0, right? And so a degree 2 polynomial would represent these terms, coefficients W0, W1, W2, these terms, so that's degree 2 polynomial. And then the degree 10 polynomial would be all of these terms where Q is equal to 10, and all of the coefficients WQ, WQ minus 1, W2, W1, W0 are non-zero. And so a degree 2 polynomial is nothing more than a constrained version of a degree 10 polynomial, where for all of those coefficients greater than W2 or greater than the second one, they're all zeros. And so that's a pretty hard constraint, because when you make a constraint in that following fashion, all you can do is draw polynomials that look like some form of quadratic. Maybe the quadratic is tilted, or maybe it's further up or further down, or maybe it's more eccentric, scoops more vigorously based on the coefficients, but it's not very descriptive. Another version of the constraint is the so-called soft constraint. And the soft constraint is as follows. You take your terms and you have a weighted sum, like in this case, you take all of your coefficients, you square them, for Q goes from 0 to the degree of the polynomial, and you write WQ quantity squared less than equal to some budget C, or some so-called soft constraint. And what that's doing is when we write our polynomial, W0 X0 plus W1 X1 plus W2 X2 plus, that should be an X2, plus let's say WQ XQ. Now, what that's doing is, imagine you have a number C, and C is a budget or a certain amount of weight. Now, what you're doing, you're basically taking this C, and imagine if you're dividing that C, kind of chopping it up into pieces, and say, okay, well, X0 is going to get this piece, W10, the 10th term is going to get that piece, this next piece, that's going to go to X2, this next piece. And so imagine chopping this up into pieces, and each of these weights gets a piece of that total weight. You're sort of handing it out from a budget. And once you get C units of weight represented among all these weights for your degree Q polynomial. You can't give out any more. So what does that do? Well, what that does, if C is big, if C is a big number, well, you have a lot more weight, and your W Qs are going to be bigger, right? Your individual weights. Now, if C is small, what that means is that budget is going to be very tiny. It's going to be really small. So when you chop it up into pieces to give out, you're going to have a smaller amount of weight to give out. So that means your WQs are going to be small, right? And the interesting part about this, rather than cutting off particular terms, you can have a little bit of the type of descriptiveness of a degree Q and a degree 2, a degree 1, degree 10 polynomial, but you're sort of lessening the amount of weight that you're giving out. And so in that fashion, with this budgeted version, you effectively have use of the descriptiveness of all of the or degrees, if you will, for that polynomial. So you can have first order wiggliness in your polynomial, second order, third order, fourth order, up to including qth order. With even a very small budget, you still can kind of hand out that in very different places instead of just cutting it off at degree 2. Okay? All right. And so this so-called soft version of the constraint means that the bigger the budget, the bigger the weights are, because you can give out more budget to different coefficients. And the smaller this budget, the C, the smaller the weights are, because you don't have as much to give out. So now what you do is you can recast this minimization problem and now introduce this constraint so that you find solutions that are within this budget while still minimizing in-sample error. And so it changes then this optimization to be that same minimization. So we still have that minimization, but now we introduce this constraint subject to W transpose W is at most C, which is exactly what this soft constraint is doing. Because if we take our W vector to be a column vector, and that column vector is going to have our W0, W1, WQ. So these are the different coefficients of the degree Q polynomial. That should be big Q. Then, of course, if I write W transpose W, that's nothing more than this weighted sum. And we're checking that against less than equal to our budget C. All right, so here we change our constraint to be W transpose W at most C. And our solution, therefore, is now the WReg, the regularized version of regression solution, which is going to be different instead of the original WLin that we had from before. Okay? All right. So let's take a look at this. So let's kind of pause on this slide and habituate on this slide a little bit to discuss the intuition, and then we'll go from the intuition, this diagram, to the actual math to motivate our solution. And so what happens when we have this expression for in-sample error? Well, this in-sample error, if En is equal to some constant, this is essentially the formula for an ellipse. And we're trying to minimize this to find when En goes to 0. When En is exactly 0, that's Wlin, which is this solution, this point here. But if En is non-zero, that means it's some scalar, some constant, right? And so you have some weights, you have a squared term, you say a minus y, and essentially that looks like an ellipse of different size. And so En is a particular constant. If En is smaller, right, for each value of En, you get these concentric ellipses, right, that are either smaller or larger as this constant gets smaller or larger. And so you have a different version of En here, a different version of En there, another version of En here, right, for every constant value of En. Now, of course, if you try to minimize in-sample error, what does that mean? You're trying to make En smaller and smaller, smaller. So these concentric ellipses that you're considering, W's, such that these ENs get smaller and smaller and smaller, and eventually they come to a point when EN is 0, and that's your linear regression solution that you arrive upon using pseudo-inverse. Now, of course, when EN changes, the gradient of EN, either EN expands out in this direction if it gets bigger, and that's the change in EN. But since you're walking down the gradient, you're getting more and more negative. So you're going to be trying to encourage, when you solve for the W-Lin solution, you're going to be going in that direction. And so we talk about the gradient of EN as being this normal vector to the ellipse, and that normal points outward, right? Because when you walk down the gradient, you're doing so to try to get EN to be smaller, to go from a larger concentric ellipse to a smaller concentric ellipse, from one step to the next step to the next step. And so the gradient of EN is a normal vector to the surface of one of these concentric ellipses. And when we minimize EN and walk down the gradient, we're actually going in the opposite direction because we're subtracting, right? We're making the gradient smaller. You make it smaller by subtracting. Okay, so that's the EN. Let's take a look at the constraint. And so you're not just going to choose any solution for EN. You're going to choose a solution for EN that also respects this constraint, subject to W transpose W is at most C. And so what does W transpose W equals 0 mean? W transpose W equals 0 is this point, but W transpose W, now you notice here, is W transpose W, right? That's a perfect circle, right? So we draw that constraint as this red circle, and W transpose W equals C is the largest value for this constraint. It can certainly be less. Now, we would also have these concentric circles if we had W transpose W equals some other constant that's smaller than C, but for W transpose W less than or equal to C, the biggest this constraint can be is precisely equal to C, and that corresponds to this red circle here. Now, of course, if we were to look at changes in this constraint, a value of this W transpose W is some value smaller than C, that less than part of less than equal to, that would be a different concentric circle to this red one that can get smaller and smaller and smaller, or larger and larger. So we also draw the normal to this red curve. And now when we try to solve this minimization problem subject to this constraint, we're trying to find a value of W that gets in-sample error closer and closer to the W-Lin solution. So we want to push that solution in towards that direction. But this constraint is kind of pulling us in the other direction, right? The constraint wants to say, hey, wait a minute, but you have to make sure you're closer to that constraint line, right? Because the best way, because you cannot violate this constraint, all of your solutions to minimize EN wants to pull it in the direction of W-Lin, but you can't do so and violate this constraint, right? So one force wants to tug inward this way towards W-Lin, and the other wants to tug in the opposite direction. And so when we look at this constraint, well, the best solution you can have is essentially going to be some solution that sits along the surface of this constraint that's closest to this W-Lin solution. And so if you were to have a solution here, right, a solution here, that's W, not essentially, that is W. And if we were to actually draw a vector from the center of the constraint out through the normal, where it pierces that solution, that's exactly W, right? Because if W transpose W is equal to C, well, to get W, you can solve for it precisely. It's just the square root of this W transpose W value. So nonetheless, when we have this point W, the idea then is to select some W along this constraint that's closest to the W-Lin solution. And so this wouldn't be the solution, that present value of W, because if you look at it, you can go in this direction or this direction along the tangent to the constraint and actually get a value that's closer, right? It's this much closer to the W-Lin solution. And so that just says the best solution you can have is one for which the gradient of EN points downward in that direction, and the normal to the constraint points in the opposite direction. right? And so En, the gradient is this way, and because you're minimizing the gradient, you want to pull in that direction, but En, gradient of En, is that one. And the best solution is also in the opposite direction along this constraint because it satisfies the constraint and is closest to the WLin solution. Okay, and so one thing that can happen is, let's say your constraint, the red circle, so let me change my pen color. Let me just do it all in blue. So let's say here's my constraint, and let's say I made my constraint really big, right? The constraint was really, really big. W transpose W is equal to C. And let's say my constraint was really huge, and then my in-sample error, let's assume my in-sample error was here, and what if the WLin solution for En equals constant, and let's say that WLin solution was inside of the constraint, right? So this is my constraint, W transpose W equals constant, and let's say my En, WLin was right here. Now in that particular case, you're going to be able to get En to be exactly 0 because you can still satisfy the constraint and get the WLin solution, and that's where your En is going to be exactly equal to 0, right? And in doing so, you're effectively ignoring, if you will, the effect of the constraint because your En falls within this constraint, so you're just going to get En equals 0. On the flip side, you could have your constraint. So here's your constraint. This is your W transpose W equal to constant. And let's say your En was way out here, right? So let's say En, and this is your WLin solution, and En is equal to a constant. Okay. So in that case, well, what's going to happen? Well, the best you can do is going to be this solution, right? That's going to be your W, right? And your gradient of En is going to be this way, and your normal is going to be that way, right? And so essentially what happens here is that your constraint will tend to pull the solution away from your WLin, right? Further and further away, right? And that's if your constraint is very small, right? Okay, so in essence then, our gradient of En, which is in the opposite direction of En, is going to be proportional to the negative of the W-reg solution. So it's going to want to go in the opposite direction. So here we say the gradient of En for the regularized regression solution is going to be proportional to the negative of the W-reg of W-reg. Okay, so if we do this, let's think about this. So there's going to be a constant, we said proportional to, and for this constant, we're going to write it to make things convenient for ourselves, right? So we're going to write this this gradient here. We know that when we compute the gradient, it's the result of taking the derivative of something, and it should be proportional to the minus, so we still have our minus sign here, and we're going to make it convenient and assume because it was involved the derivative of something that was squared, we know that when we take the derivative, or this resulted from taking the derivative, we had a leading to. So we're going to make things convenient for ourselves. We're going to add this lambda upon n, and that'll be mathematical convenience, but we make the assumption that we took the derivative of something squared, so we're going to add a 2 here, include a 2 for the constant of proportionality. And so we're left with minus 2 lambda upon n times W reg, right? And we're making the assumption is that our gradient of En, in sample error, is going to be in the opposite direction of W reg, right? So this is the gradient of En, right? It goes in that direction, and W reg is going to be in this direction, Okay? All right. So we take this expression and we do a little bit of math. So we're going to have En, gradient of En, at the regularized regression solution is going to be equal to minus 2 lambda upon n w reg. And so we do a little math and add this term to both sides of equality, and that gives us the gradient of En at the w reg solution plus 2 lambda upon n w reg is going to equal 0. Okay, this gives us the gradient of En at the w reg solution plus 2 lambda upon n w reg is equal to 0. And so we subtract, we add minus 2 lambda upon n w reg to both sides of equality, and it gives us this expression, the gradient of En at the w reg solution plus 2 lambda upon n w reg is equal to 0. And so this is a minimization problem, and that minimization problem, which was originally to minimize in-sample error subject to this constraint W transpose W, is at most our budget, soft weight budget C, becomes the gradient of En at W reg plus 2 lambda upon n W reg. Now, of course, when it's equal to 0, so that's the result of a minimization problem. You minimize something that's smooth and differentiable by taking the gradient and setting it to 0. And so let's look at the original problem, and we think about what expression such that when we take the derivative and set it to 0 is equal to this quantity, this gradient En W reg plus 2 lambda over n, upon n W reg. Well, that gradient of En, if we took the derivative of something and we resulted in, for one term, the gradient of En of W reg, that's nothing more than En of W, right? Because you take the derivative of En of W, and that would give you the gradient of En at that W reg solution. The second term here, we have a 2 lambda upon n and W reg, and that's the result of taking the derivative of something. Well, what gives you 2 times some value? That's value times itself, right? So that is just the result of taking the derivative of lambda upon n W transpose W. And so if you imagine here, if we look at this term, well, if we take the derivative of that, that's just 2 times lambda upon n W. Okay? All right. And so if we look at the relationship between these two terms, we have the original formulation, which was constrained. We result in a minimization problem of something that does not involve constraints. And so it's really hard to do an optimization when you have constraints because you have to bounds check every solution that you consider. But now we have the equivalent minimization problem, and there's an equivalency between this budget C, the soft budget, and this lambda, which we call the regularization parameter. If C is really big, that corresponds to lambda being really small. And let's think about what happens when C is really big. As we said up here, if C is really big, well, you just minimize in-sample error. And what does that mean? It means what's dominating this minimization problem is this first term involving in-sample error, En W, right? And if C is large enough, then it will encompass that W-lin solution, and we're just driving En to 0. Now, of course, from the minimization problem, well, that means lambda is small. If lambda is really small, then the contribution of the second term, lambda upon n W transpose W, doesn't play very much into this minimization. It doesn't hurt as much to consider a different solution W, because this does not contribute very much if lambda is small. Conversely, we have this scenario that we considered where C is really small. Now, if C is really small, you're basically pulling your solution away from the W-lin closer to this constraint in order to keep it satisfied. And that corresponds to C, this budget, weight budget, being very small. And we said if C, this weight budget, is very small, you're going to have less weight to give out to all of the coefficients of the polynomial expansion. And that's going to result in this term dominating the description or the selection of the weights, because it's going to pull away from this in-sample error and move more just like W's that satisfy this constraint. And so that corresponds to this lambda being very large. And so C is small, lambda is large, and that means this term, this constraint, is dominating more the direction of this optimization. Okay. So We call this an augmented error metric, E augmented, and it's nothing more than our expression for in-sample error plus this penalty term. And this, if we were to expand this in vector matrix form across your entire data set using a design matrix with all of your in-sample points mapped to Z-space, feature space, that would be 1 upon n ZW minus Y transpose ZW minus Y, and then we add this penalty term, this regularization, lambda upon n, where lambda is the regularization parameter, W transpose W. And so this expression, it's an optimization problem. It does not have any conditions, and therefore we can solve this in closed form as a regression. That's in contrast to the constrained version. It has conditions. The interesting part is that this condition version, this C, almost acts like a VC dimension. It allows you to talk about complexity the same way you would talk about complexity in the form of a VC dimension. And in essence, that makes sense because the bigger that C is, the more weights that you can give out to each one of those polynomial terms, and the more weights for the coefficients you give out to the polynomial terms for all of those degrees in the polynomial, the more complex that polynomial is going to be, because it can now twist and turn and bend and fold in a more dramatic way because those terms are counted more if C is bigger. So let's take a look at the regularization, the regression solution for this augmented version. So we say we minimize E augmented, which is En plus our regularization penalty, lambda upon n W transpose W. So we expand what that means. And another benefit of including that 1 over n in this regularization penalty, in-sample error has this leading 1 over n, and it kind of fits nicely for this regularization penalty in the same expression. So we have this 1 upon n. We bring that common 1 upon n out, and we write our ZW minus Y transpose ZW minus Y plus lambda W transpose W. And the goal then is to minimize E augmented. So we take the gradient and set it equal to 0, and then we solve for W in similar fashion to how we did it for linear regression when we arrived upon pseudo inverse. And so we do that gradient, and so here we have a squared term, and how you compute a squared term, okay, you have 2 times this expression times the derivative of of one term with respect to W. That gives us, okay, well, we have a Z W minus Y, and then we compute the derivative of, with respect to W, of ZW minus Y. So that's just Z, because that's the only term that has W, is this Z term. So we have Z transpose ZW minus Y plus lambda W, right? And there's a leading 2, but because we set this equal to 0, we can divide by, multiply both sides by 1/2, and the 2 goes away. So we have this 1 upon n, we have this Z transpose ZW minus Y plus lambda W equals 0. Now this leading 1 over n, we can just multiply both sides of equality by n, and that n goes away because 0 times n is 0. Right, so we have this Z transpose ZW plus lambda W is equal to 0. Okay, so we do that, and let's multiply this out. So if we multiply this out, that's Z transpose ZW minus Z transpose Y plus lambda W is equal to 0. So now, if we bring this Z transpose Y over to the other side, what we get is Z transpose ZW plus lambda W is equal to Z transpose Y. So now we factor out the W for that term on the left-hand side of equality. We get W times, or actually we should say it this way, Z transpose Z plus lambda times identity W, get rid of that, is equal to Z transpose Y. And so now we take the inverse of this expression, and we solve for W, and that gives us the W, what we're calling W reg, which is the regularized. We take the inverse of this expression, and that gives us a solution for W that we're calling W reg, and W reg is the regularized regression form. And so that's W reg is equal to Z transpose Z plus lambda times identity quantity inverse Z transpose Y. And it's the regularized version of the linear regression solution, where W-lin is just our usual pseudo-inverse. That's without regularization. And so the impact of regularization is this term, right? If you add to lambda, that's going to impact your solution. If your lambda is larger, it's going to be smaller. If your lambda is smaller, then it's going to dominate with the Z transpose Z term. Okay. So let's take a look at what this might mean. So here is the minimization problem, and we go back to that problem that we stated at the outset, where we have a target function which is quadratic, and we have a fourth order polynomial as our hypothesis set. And this quadratic, we're going to sample data and add noise to it, 5 data points, and do the fit. And so with no regularization, our lambda is 0, our regularization parameter. That's no regularization, it's unconstrained. We do the fit, and we get that overfitting solution that we had from before. With just a little bit of regularization, we set lambda to 0.0001, and we do that same fit. So what that's doing is increasing the little bit of the weight. Instead of just E in going to 0, it has to pay attention to the constraint a little bit. And in doing so, we look at much more dramatic solution. We get a pretty good fit, and that fit looks a lot like the second order polynomial fit. Very interesting. All right, so if we increase our regularization parameter even more, we get this behavior. It's starting to get worse. It's starting to get worse. And essentially what's happening, it's starting to so-called underfit, right? It's paying attention so much to this penalty, this regularization term in the optimization, and less so to the minimization of En. Now we get out of sample error starts to increase, and that's overfitting. And you'll also notice when it's overfitting, this model gets more and more simple, right? Eventually it would flatten out into a constant line and not be so good. All right. So let's take a look at weight decay, and we'll end with this weight decay. And what weight decay means is that over time, what this regularization parameter ends up doing is decreasing or decaying your weights. And so here we have the minimization problem, En plus lambda upon n with a regularization penalty, W transpose W. And because of gradient descent, what do you do with gradient descent? Gradient descent says you take your current weight value, and to compute your next weight value, you're going to subtract the gradient of this augmented error term. So that's going to be eta of this gradient of En at the current weight value. And then we also have our lambda over n W times the weight vector W. And so we subtract this through a learning rate eta, and we collect our terms. So we have W at time step t plus 1 is equal to W time step t minus the gradient of this expression, right? So we have minus eta times the gradient of En minus eta times 2 lambda upon n, right? So that's the gradient of this W transpose W term, right? So if we take this expression and we collect like terms, W t, so we have this WT term, so that's, call that the first term, call that the second term, and we'll call that the third term. Well, if we combine terms, well, we look at term 1 and term 3. So that's term 1, that's our WT, right? And we collect them together. And this is our third term, is we have the 2 eta lambda upon n. So that's our third term. we collect them together, factor out that common w at time step t. And so the next term, this is just the second term from up above, that's the minus eta gradient of E in w at time step t. So if we do that, we pay attention to this step. And essentially what it does is it shrinks the weights. It moves the weight and then it shrinks the weight and then it moves it. And so here it ends up, if you subtract this value from 1, that's going to be a value that's less than 1. And if you multiply a value less than 1 times that weight, it's going to end up making the weight smaller and smaller and smaller. Now, smaller weight corresponds to smoother solutions, because if you imagine we had, going back to the beginning, if we had WQ x to the q power, if we had ... up to, say, W2x to the second power, W1 x to the 1 power, plus W0 x to the 0 power, if your W's tend to be smaller, what ends up happening, your weight vectors tend to be smaller, what ends up happening is you get smoother solutions, because these polynomial terms, these exponentiated terms, these monomials in your polynomial, the effect will be less, and you end up not moving and bending and folding quite as rapidly. And so that results in smoother solutions, which is exactly how regularization constrains your models. So here we have this step when we walk the gradient in gradient descent. The impact of this penalty term, this regularization, is to decay your weights. It makes it smaller, and then it moves down the gradient. Makes it smaller, and then it moves down the gradient. This is also the case in a neural network. In a neural network, we have similar constraint. W transpose W corresponds to, for all of the weights, so this is going by the layer, right, from 1 to big L, going from the input node in layer L minus 1, 0 to the dimensionality of layer L minus 1, to the node in layer L, J, that index from before, goes from 1 to D superscript L, which is dimensionality for layer L. And we square each of these. That's the same as writing out all of your weight vectors for all of your weights in one big vector for your neural network, and just computing W transpose W. Right? And so you can absolutely have this regularization penalty in neural networks. Okay. And so another thing you can do, especially in neural networks, so-called Tishanov regularization, is you can add a term to your coefficient to regulate which part of your model gets decayed to emphasize certain parts of your weights more than others. And here we have our definition of our polynomial, and we're going to modulate each weight with this other modulating term. And so we can have weights W0, W1 up through W big Q corresponding to each of the order for terms in the polynomial. And if our gamma is structured as a 2 to the q, well, as q gets really big, i.e. a higher order term or weight corresponding to a higher order term in the polynomial, well, that's going to hurt more, right? So that means the contribution for a higher order term is going to add a lot of penalty to your optimization. And so what that ends up doing is putting emphasis on the low order terms in the polynomial, so that the model favors the low order factors, because it's not going to give a lot of weight to terms for the high order, because it's going to add a lot of penalty to your optimization, and its minimization is not going to want to prefer to add weight there in those parts of your model. And so conversely, if your gamma is 2 to the minus q, that's going to be a higher order fit. And so if you have your q, your order, being larger, well, this is going to be a much smaller value, right, decays, and that means the higher order terms, WQ, are going to contribute less penalty to your minimization problem. So it's going to tend to want to fit or want to count more or add or put more weight budget into the weights corresponding to high order terms. And so here the penalty will emphasize low order terms, so the model favors the high order factor. And in the first case, the penalty emphasis was on the higher order terms. So your model, when you're minimizing, it's going to favor low order factors. And in a neural network, you can have different layers get different gammas, and this is called Tishnov regularization. Here, capital gamma is just a matrix where the layers, the diagonals along the gammas will select out different penalties, if you will, for different layers, so you can place different emphasis on the layers. And so you could, if those gammas favored more the lower layers on the neural network, that would favor more weights on the features. If it favored the higher layers in the network, that would favor the assemblies of low-level features into things like, if you're dealing with images, things like shapes and faces and things like that versus edges and pixels. Okay, so large weights are typically bad. And when you look at the nature of noise, we talked about noise as being organized into two categories, stochastic noise and deterministic noise. Stochastic noise is generally high frequency, and deterministic noise is also not smooth. And when you add a regularization penalty, you're effectively constraining learning in general towards much smoother hypotheses. So smaller weights correspond to smoother hypotheses. So if you take your regularization parameter, and you have your model, and you start increasing your regularization parameter here, what ends up happening is your weights start getting smaller, 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 and smaller. And then eventually you increase your regularization parameter too much, and that's pulling away from that W-lin solution, and then you start underfitting, and your expected out-of-sample error starts to increase. Now, of course, if your weights were growing instead of shrinking, your expected out-of-sample error would just skyrocket from the beginning, regardless of what your regularization parameter is. So you start in the beginning overfitting, and then you're good in your operating regime, and then you start underfitting, and that underfit, too much of a good thing, leads to bad out-of-sample performance. Okay, so hypotheses can have regularizers, and let's call this regularizer our omega, and omega is going to be specific to a particular type of hypothesis, and we pose this augmented error, EAUG, which is just your in-sample error plus this penalty term, and we added this scalar to it, lambda upon n, where lambda is a regularization parameter. And so this kind of looks a little bit like something we've seen before. Before we talked about out-of-sample error, and we looked at the relationship between in-sample error and out-of-sample error through a complexity measure, and that complexity measure was over the hypothesis set. And that's what we arrived upon when we talked about the VC bound. Right, so the VC dimension talks about the complexity or the descriptiveness, if as it were, of the hypothesis set. And so here we said E out is related to E in, bounded from above, including this complexity term. And likewise, we say augmented error is better than E in as a proxy for out-of-sample error. Right, so this augmented error, it almost looks like something we've seen before when we talked about the VC bound. So because the augmented error version considers complexity of the function, you can think of that regularization as defining complexity. The smoother the hypotheses, the more constraints, the less complex it is. The less smooth the hypotheses, the fewer constraints, the more complex it is. And so this augmented error, this regularization penalty, it almost looks like a complexity term, but it kind of works in the inverse, right? If lambda is big, it's going to be less complex. If lambda is small, it's going to be more complex. Whereas here, if omega is big, it's more complex. If omega is small, it's less complex. And so it looks like the complexity of functions, and it's a much better proxy for E out because it's able to produce this penalty term. It's able to cause your augmented error minimization to choose smoother solutions, which are more simple, less complex. Okay, so let's end there, and we'll pick up with the balance of this on